In America, we take pride in having the right to our own opinions, and that's a great thing. But somewhere along the way, we started to forget that opinions are supposed to fill in the gaps between facts, not replace them. The problem comes when we decide which facts we'll accept and which we'll reject, based on whether or not they agree with our worldview. If a fact challenges what we believe, the healthy thing to do is update our worldview to match the facts. But far too often, we try to change or deny the facts just to keep our worldview intact. We tell ourselves, well, I don't understand it, so it can't be true. Or, if nobody I know can explain it, then nobody can know it. And because we're social creatures, we assume that if a lot of people believe something, that makes it more likely to be true, even though reality doesn't work that way. The lines get blurry. Many of us start treating opinions as facts and facts as opinions. The only facts we accept without a fight are the ones that don't threaten our beliefs. The moment they do, we call them just opinions and feel no need for evidence to hold on to our own view. But if those same facts challenge us, suddenly we demand mountains of proof, and even then, no amount is ever enough to change our minds. When these controversies show up in science, it gets even trickier. From the outside, it might look like someone is challenging mainstream science because they care about the field, but in reality, they're often just defending an opinion that's already been disproven by specialists for years. They cherry-pick data that supports them, then demand that anyone challenging them cherry-pick a single fact to disprove them. That's not how it works. One fact, in isolation, doesn't prove or disprove anything. It's the entire tapestry of evidence, the big picture, that shows what's true. And that's exactly why science is divided into branches, why experts spend years mastering one specialty, and why someone respected in one field isn't automatically an expert in another. The truth is, science is complex. And the people most likely to deny or distort it are the ones who oversimplify it because they don't understand it. That's the breeding ground for pseudoscience, and it thrives wherever complexity is ignored in favor of simple, comforting answers. Science does challenge itself, constantly. That's its strength. But there's a huge difference between how science challenges science and how pseudoscience challenges the whole body of science. They look similar on the surface. Both involve someone saying you're wrong. The difference is everything: method, evidence, motive, and outcome. Think of science as a building made from thousands of bricks, data, experiments, models, and repeated checks. When scientists challenge the building, they don't try to blow the whole thing up with an unproven claim. They bring a new brick, or a stronger mortar, or better blueprints. They test a new idea against the existing structure. If the new idea explains more facts, more accurate predictions, and if independent teams can replicate it, then the building gets remodeled. That's how real scientific change happens. Careful, cumulative, peer-checked. Pseudoscience, by contrast, shows up with a crowbar and says, the whole building is fake. It usually proposes a sweeping alternative, one that, if true, would overturn many well-established results. And then it demands that you accept that alternative without doing the work that real science requires. The crowbar approach sounds dramatic and decisive. That's why it's seductive. It promises simple answers to complex questions. But it doesn't play by the rules that produce reliable knowledge. Here's how to tell them apart, in detail. 1. Standards of evidence, incremental versus extraordinary. Science challenging science proposes a hypothesis, collects data, and evaluates whether the hypothesis improves explanatory or predictive power. It uses controlled experiments, statistics, peer review. When a claim is extraordinary, e.g. diseases are caused by invisible spirits, or aliens engineered humans, the evidentiary bar goes up accordingly. Good science recognizes that extraordinary claims require proportionally extraordinary evidence. Pseudoscience makes extraordinary claims but uses ordinary or anecdotal evidence. It cherry-picks cases, misuses statistics, cites isolated items as proof, or relies on testimonials and viral videos. It rarely produces reproducible experiments or predictive models. 2. Falsifiability and predictive power. Science? A useful scientific claim makes testable predictions that could be falsified. If those predictions fail repeatedly, the hypothesis is revised or abandoned. Science prizes models that make precise, risky predictions, because those are the ones that can be proven wrong and therefore proven useful. Pseudoscience often creates stories that are unfalsifiable. When a prediction fails, the explanation is moved or wrapped in ad hoc excuses. They covered it up, the artifact was planted. It's a spiritual truth beyond science. There's no real predictive power. 3. Method and reproducibility. Science. Methods are specified in detail so other researchers can reproduce the experiment. Reproducibility is a cornerstone. Independent verification is required. Pseudoscience relies on one-off observations, poorly documented field reports, or private procedures. When others try to replicate, the original claim often evaporates or the replicators are accused of being part of a conspiracy. 4. Engagement with existing knowledge. Science builds on existing bodies of knowledge. A new theory must account for the successes of the old theory as well as fix its failures. It integrates across disciplines, biology, physics, geology, or explains why previous results were misinterpreted. Pseudoscience usually ignores, dismisses, or misinterprets existing literature. It treats the entire scientific enterprise as corrupt or incompetent rather than offering a better, more comprehensive model. Often it replaces a broad, interlocking body of knowledge with a single simple story. Number 5. Peer review and community vetting. Science. Hypotheses are exposed to critique by many experts. This doesn't mean miracle consensus. It means open critique, replication attempts, statistical checks, and methodological scrutiny. Pseudoscience bypasses peer review, or manufactures fake journals' praise, tells supporters to do your own research, conveniently on unmoderated platforms, and fosters communities that reward confirmatory anecdotes instead of critique. Number 6. How change actually happens in science, and why it's conservative. Real scientific revolutions, heliocentrism, germ theory, plate tectonics, weren't spontaneous rejections of the whole system. They emerged because 1. New, reliable observations accumulated that contradicted the old framework. 2. Independent groups replicated results. 3. The new theory explained more phenomena and retained the successes of the old theory where appropriate. 4. The community gradually adopted the new framework because it worked better in practice. Science looks conservative because it must be. The existing body of knowledge explains an enormous array of phenomena and powers technologies we rely upon every day. You don't overturn that lightly. 7. Motivations and incentives. Science. Incentives reward accuracy over grants, reputations, and careers depend on producing reliable, reproducible results. While science has institutional problems, its structure incentivizes correction. Pseudoscience. Incentives often reward attention, simplicity, and novelty. Viral claims, book deals, and monetized channels reward spectacle. That shifts motivation from what's true to what sells. 8. Common pseudo-moves that mimic scientific rhetoric. Cherry-picking data, presenting correlation as causation, invoking conspiracies when challenged, using scientific jargon without rigorous method, equating dissent with censorship, presenting isolated anomalies as definitive proof. These moves sound scientific because they use surface features of science, a graph, a fancy term, and appeal to data, but they lack the process that turns data into knowledge. 9. Practical checklist. How to evaluate a challenge. When someone tells you science is wrong, ask 1. What is the proposed mechanism? How would this actually work in step-by-step terms? 2. What are the testable predictions? Can I design an experiment that would show it's false? 3. Has the claim been replicated by independent teams? Or is it a single source? 4. Does it integrate with well-established facts? If it contradicts many well-tested results, how does it explain those? 5. Is there peer review or published methodology? Not just blog posts or YouTube. 6. Who benefits if this claim is believed? Monetary, social, ideological incentives. 7. Are ad hoc excuses used when predictions fail? This is a red flag. If the answer fails in multiple places, you're probably facing pseudoscience, not a legitimate scientific challenge. 10. How pseudoscience audiences conflate the two. Pseudoscience audiences often point to real historical examples where science was initially wrong, like continental drift or germ theory, and say, see, science is always overturned, so my theory deserves the same treatment. That's a false equivalence. The difference is not that science was once wrong, everyone accepts that, but how the correction came about. Plate tectonics wasn't accepted until multiple independent lines of evidence, seafloor spreading data, paleomagnetism, earthquake distribution, converged and produced a model that solved many previously unexplained problems. That's different from positing a single flashy claim with no converging evidence. Communicating the difference. Short scripts you can use in video or conversation. Questioning is healthy, but the question is how you're testing your idea. Do you have a method that others can replicate? What would show your idea is false? If a single example is your whole argument, that's not how science builds knowledge. Show me the body of evidence and how it connects. Extraordinary claims require extraordinary evidence. Saying it could be aliens doesn't meet the evidentiary standard needed to change everything we already know. 12. Finish with an analogy. Imagine medicine as a massive old tree, grown from centuries of observation, trial, and correction. If someone claims they can fell the tree with a single blow of a machete and offers only a blurry photo and a personal story, you wouldn't trust them. If someone brings a new, rigorously measured method that, after independent testing, proves safer and more effective, we'll all adopt it. Science is the latter: incremental, tested, and communal. Pseudoscience is the machete pitch. In short, science does challenge itself, but it does so by building evidence, making testable predictions, and submitting ideas to independent scrutiny. Pseudoscience dresses itself in the clothing of science while refusing the method that makes science reliable: reproducibility, falsifiability, integration with the rest of our knowledge, and an exceptionally high bar for overturning well-established results. Recognizing that distinction is the single most important skill for anyone trying to separate true innovation from clever noise.